cosmological scales, on large scales, is more or less homogeneous and isotropic. So let me go through these fundamental pillars. I would like to first start with general relativity and introduce it. Hopefully, I will introduce it in a rather complementary manner, and maybe some of these perspectives might also useful or new to you. Otherwise, you can then just check your emails or do whatever you feel like. Okay, so I would like to represent general relativity from two complementary perspectives. The first one is going to be the geometrical representation of general relativity, and then I will move on to the particle representation. Let me start with the geometrical representation. And there, the fundamental geometrical objects are the curvature, the torsion, and the non-metricity. So these three geometrical objects will allow me to introduce the geometrical trinity of general relativity, where you can find more information in this paper if you are interested. So the first one is, of course, the standard representation of general relativity based on curvature, a la Einstein. But I will introduce a second formulation of general relativity based on torsion. This is the teleparallel equivalent of GR. And finally, I will introduce yet a third geometrical representation of general relativity, this time based on non-metricity. What are these geometrical objects? What do they physically represent? So you already are familiar with what curvature represents. So if you have a space-time with non-vanishing curvature and you have a vector pointing towards the direction, and now you move it along a closed path and you come back to where you started, but now this vector points towards a different direction than you started with, it means that your space-time has a non-vanishing curvature. How about torsion? So now if you have two vectors and you parallel transport them along each other, and if this parallelogram doesn't close, it means that your spacetime has a non-vanishing torsion. And similarly, what is non-metricity? So now if you have a vector pointing towards the direction and you move it along a given path, then its length changes if the manifold has a non-vanishing non-metricity. Let me then introduce general relativity first, a la Einstein, the standard formulation. In this case, we have a pseudo-Riemannian manifold, where our fundamental object is the metric, this metric G mu nu. And the connection, which are represented by this gamma alpha mu nu, is simply given by the Christoffel symbols, given by this curly brackets, which is completely determined in terms of the metric. Now you live in a space-time which is completely curved. So the Riemann tensor is non-zero, but torsion is zero and non-metricity is zero. So you have to work with the Riemann tensor, with the curvature tensor. And its form is given here. You see, you have some Christoffel squared part, but you have also some derivatives acting on the Christoffel symbols. And so you have here a tensor with 4 indices. You can simply contract these indices and build a scalar quantity. And in this way, you uniquely get the Einstein-Hilbert action. And because of these derivatives acting on the Christoffel symbols, you have second derivatives acting on the metric. And that's a problematic property, let's say, of the standard formulation of general relativity. For instance, if you do the variational principle, then you need to have a the Gibbons-Hawking-York boundary term in order to have a well-posed variational principle. So this difficulty comes from having second-order derivatives acting on the metric. Let me move on to the teleparallel equivalent of GR. In this formulation, you have a manifold based on torsion. Now, the fundamental object is the connection, not the metric anymore. And the connection has this important piece, which is the contortion tensor, given in terms of the torsion tensor here, like this. Now you live in a space-time which is completely flat, curvature is zero, and non-metricity is zero, and only the torsion is non-zero. Here is the definition of the torsion. So torsion is the antisymmetric part of the connection. So it has, because it's the antisymmetric part, so it's antisymmetric in this mu indices, and you see it's a tensor with 3 indices. You cannot build a scalar quantity at linear order, so you have to go to second order in torsion. And because it's antisymmetric in mu, you have 3 independent contractions at the quadratic order in torsion that I am denoting here. 1, 2, 3 independent contractions with some arbitrary coefficients C1, C2, and C3. And with some Lagrange multipliers, I also make sure that my conditions are satisfied, that it's flat, and that it's non-metricity free. And only if you choose these arbitrary coefficients in this very specific way, you obtain an equivalent theory to general relativity with 2 propagating degrees of freedom. So if you want to relate now this quadratic torsion scalar with these coefficients chosen in that very specific way, you can relate that to the Ricci-Curvature scalar of the standard Einstein-Hilbert action in terms of the Christoffel symbols. And you see the relation is up to some total derivatives, up to some boundary terms. So they are equivalent at the level of the equations of motion, but at the level of the Lagrangian, they differ by total derivatives. Let me move on to the coincident general relativity. Now you have a manifold based on non-metricity. Your fundamental objects are both the metric and the connection. And now the connection has this important piece here, the disformation tensor, given in terms of the non-metricity tensor in this form. You live again in a space-time which is completely flat, so curvature is 0 and torsion is 0. And the non-metricity is the only available geometrical object. Here is the definition of the non-metricity tensor. So it's the covariant derivative with respect to a general connection, which is not the Christoffel symbol, acting on the metric. So this is the non-metricity tensor. And the fact that we have curvature and torsion being 0 has huge consequences. So by means of gauge choice, what one can do in this coincident general relativity formulation is that one can completely get rid of the connection. This you cannot do in the other formulations by means of a gauge choice, but in coincident GR, this is possible. This is the coincident gauge. So as I said, okay, this is the definition of the non-metricity tensor. Now again, you see it's a tensor with 3 indices. Now it is symmetric in the mu indices. Again, at linear order, you cannot build a scalar quantity. You have to go to quadratic order in this non-metricity tensor. And because it's symmetric in the mu, now you have 5 independent contractions with 5 free parameters that you have to choose. And with Lagrange multipliers, we again make sure that we have flat space-time and that the space-time is free of torsion. And only if you choose these 5 coefficients of these contractions in this very specific way, you obtain an equivalent theory to general relativity with just 2 propagating degrees of freedom. And again, if you want to relate it to the standard Einstein-Hilbert Ricci scalar of the Christoffel symbol, the relation is again given in terms of some total derivatives. Okay, so let me, before I mention a few properties, so in the coincident gauge, so as I said, when you choose this specific gauge where you can get rid of the connection completely, then this quadratic non-metricity scalar is exactly equal to the Christoffel squared part of the original Einstein-Hilbert action. So you get rid of this derivatives acting on the Christoffel symbol part. So let me mention a few nice properties. So there is no need for the Gibbons-Hawking-York boundary term for a well-defined variational principle in that formulation. And there's also more direct contact with the particle description of general relativity, to which I will hopefully come in a few minutes, why I am claiming that there is a more direct contact. And this improved action principle can actually make some differences when you consider some energetics, thermodynamics, or quantum theory. So like when you compute the entropy of a black hole or some other properties. So there will be some differences in these three formulations. And in the coincident gauge, of course, then since the connection is zero, this might be useful for some concrete computation purposes. So this was now only the gravity sector. How about the coupling of matter? Because this is also something very fundamental. So as you might know, the very construction of general relativity, a la Einstein, relies on the minimal coupling principle. So the minimal coupling principle is a fundamental principle. So if you have some fields, they are just minimally coupled to gravity in the sense that they only couple to the metric or the determinant of the metric, but never to the derivatives of the metric. Now, imagine you try to apply this minimal coupling principle to the other formulation. So how about the teleparallel equivalent of GR? When you try to naively apply this, you see that it doesn't work. So non-minimal couplings to torsion arise, even already for gauge fields. Imagine you have some photons, some gauge fields, and you see they want to couple to torsion. And in this way, you wouldn't have matter fields behaving in the same way as in standard general relativity. How about coincident general relativity? When you try to apply this minimal coupling principle there, it works. So the minimal coupling is preserved and the gauge fields have exactly the same geodesic equations as in standard general relativity. For fermions, the situation is even worse. In the teleparallel equivalent of GR, so torsion, as soon as you have torsion in your manifold, fermions really want to couple to it. You need to do some ad hoc things from the very beginning in order to make them not couple. But in the case of the coincident GR, if you have fermions, if you have some standard Dirac Lagrangian, then the non-metricity drops out and the fermions couple exactly in the same way as in standard general relativity. So concerning this equivalence and staying within GR works only for these two formulation for GR and for coincident GR. So this was the geometrical representation of general relativity. Let me now move to the particle physics perspective. Now, instead of talking about geometry, you are talking about particles. And so in the same way as we have the electromagnetic interactions because they are exchanging photon particle, we have now the gravitational interactions because we are exchanging a graviton particle. So in this particle representation, GR is given uniquely by a massless spin 2 particle. And this is really unique. It's not like in the geometrical one where I already showed you 3 equivalent formulations. In the particle one, this is really unique, and it's the massless spin 2 field. Why massless spin 2 field? Well, we can gather together the facts that we already know about gravity. So we know it's long range, so the particle associated to it should be massless. It exists as a classical theory, so it cannot be a fermionic particle. This excludes already the spin 1/2 type of particles. It is attractive, so it cannot be photon-like, no spin 1 particle. And it attacks with light, so it cannot be Higgs boson-like. This includes spin 0 particle. So this leaves massless spin 2 particle as a natural candidate. So how do you then construct this massless spin 2 particle, which I have denoted here by this symmetric h mu. So you write down the quadratic Lagrangian with all the possible contractions. So quadratic in the partial h, and you have 1, 2, 3, 4 independent contractions. And demanding that this massless spin 2 particle has only 2 propagating degrees of freedom, as we have seen in Shinji's talk. So this fixes directly these 4 coefficients in this very specific way. Then in this way, you obtain your linear diffs. You have your propagator. And now what you can try to do is to build interactions. So now you take this quadratic action and compute its own T mu, and then couple it to itself. And then you add it to the new Lagrangian, which is the previous one, plus H mu coupled to the self T mu. So now you have your cubic interactions, and you can now do this bootstrapping order by order. So now you go and you take this as your starting Lagrangian, you compute the T mu alpha beta associated to that, and then you couple it to itself. And when you do this bootstrapping, you see that you have an infinite series of interactions, which you can sum. So there are different techniques to sum this infinite series. And when you do that, what is remarkable is the action that you get is actually the coincident general relativity in the coincident gauge. It's not the Einstein-Hilbert action of the standard formulation of GR, where you have exactly these partial derivatives acting on the Christoffel symbols. So this was the reason why I was saying it has more direct contact to the particle representation, because when you sum this infinite series, you actually obtain the coincident general relativity action in the coincident gauge. Okay, so it doesn't matter from which perspective you come, from geometrical or from field theoretical. Now you want to model the universe. You want to build a model of the universe. So you need to solve Einstein's field equations. G mu equals to T mu, where T mu are all the matter fields. But these equations are not so easy to solve. So you need some simplified assumptions. And there our second pillar that we had introduced comes to help, the cosmological principle. Now, assuming that the universe is homogeneous and isotropic, we can actually solve Einstein's field equations. And these are these FLRW models, in which the metric is given at the background level in terms of a scale factor that only has time dependence. And because we have only a cosmological constant apart from the metric, which satisfies automatically my SO3 symmetry of the background, I can then model my universe. So these are the Friedmann equations that I obtain if I plug in this ansatz in the Einstein's equations. And I can, of course, I have also equations of motion of the matter fields. And I can solve them, and I can parameterize my Hubble function in this specific way here, where omega matter is the energy density associated to the matter fields, this one associated to the cosmological constant, and so on. So I can take this Hubble function. You see here is also H0. This is the Hubble function valued today, so at redshift equals today. And observations then indicate or prefer this lambda CDM model, in which, as you know, 68% comes in form of dark energy and 25% in form of dark matter. This lambda CDM model works very, very well, nicely, apart maybe from this H0 tension that recently received quite some attention. So when you compare the early universe cosmology with the late time universe, the value of H0 seems to be in slight disagreement. But apart from that, this lambda CDM model works quite nicely. Okay, we have also the CMB. So these are the photons released from very early universe, and they more or less after the last scattering surface propagate to us freely, and we observe them. But what we don't understand is if you take two patches on this CMB sky very far from each other, how can they have exactly the same temperature fluctuations up to 10⁻⁵ if they have never been in causal contact in the past? So how can causally not connected regions have the same fluctuations? And in order to explain that, we introduced the inflaton field that gives rise to an early phase of accelerated expansion. So this is our standard model. We have GR, dark matter, dark energy, and the inflaton field. And with this, we can describe the origin and the evolution of the entire universe. There are some fundamental questions associated to these ingredients, of course. Otherwise, we won't be having this workshop here. So what is the quantum nature of general relativity? What is the origin of dark matter? And what causes these two accelerated expansion phases of the universe? And is dark energy just a cosmological constant, or is it also a field, like a quintessence field, evolving in time? So in order to answer this question, some people, what they do is they introduce new additional degrees of freedom. So some effective field theories in which you have the standard degrees of freedom coming from GR, plus some additional fields like scalars, vectors, some maybe Young-Mills fields, and so on. In order for the purpose to explain some of these ingredients, maybe dark matter, or maybe dark energy, or both, or the inflaton field. So the scalar field, especially the Galileans or their covariance versions, have been investigated quite a lot in the literature. So these effective field theories can be constructed by demanding these following conditions. You want to have second-order equations of motion, which is useful in order to avoid some instabilities. You want to have your Lorentz invariance, locality, and for some historical reason, this scalar field also has some shift and Galilean symmetry. And in this way, you can construct all the allowed interactions. These are the Galilean interactions. You see that the scalar field comes with some second derivatives acting on it, some traces of it. And in L4 and L5, you see also there are some tuning of the relative operators in order to really satisfy this condition and have only one propagating degree of freedom. So with the scalar field, it's very easy to realize the cosmological principle, one of the other fundamental pillars that we had, by just simply having a scalar field that has time dependence. With that, you can then construct easily cosmological solutions with scalar fields. You can also construct effective field theories for a vector field. These are the generalized Procca theories. You do basically the same thing as you did for the scalar field. So, let me see. So when you assume second-order equations of motion, Lorentz invariant and locale, and 3 propagating degrees of freedom, 3 because this vector field is massive, then in this way you can construct all the allowed vector interactions. You see the vector field appears again with some derivatives acting on it. And the operators also have to go to some tunings in order to satisfy these conditions. But in this way, you can also build your effective field theories for a vector field. So it was believed that a single vector field is in tension with this, one of our fundamental pillar, namely the cosmological principle, that you cannot have homogeneous anisotropic solutions with one single vector field. And therefore that it wouldn't be useful, for instance, for dark energy purposes or for some cosmological purposes. But with this generalized Procca, this has initiated a radical change of view, because you can now have dark energy applications directly from this effective field theory, which is homogeneous and anisotropic. Here, the field configuration, the way how you realize the cosmological principle is given here. So where your vector field has only a time-dependent temporal component, which is not dynamical, but plays the role of an auxiliary field and gives rise to homogeneous and anisotropic solutions. So just to give you a very simple example, imagine you have this simple Lagrangian with a kinetic term of the vector field. some functions of the mass term, and then some cubic type of Galilean interactions. Then with this simple action already you can have dark energy fixed points. So this vector field plays the role of dark energy. And we have also actually shown that it reduces the H0 tension and delivers a better fit to data. So how am I doing with time? I believe I have 5 more minutes.
Yeah, I have you starting at 13:48.
Okay.
So you have, sorry, it's hard to calculate.
Okay, I have like 7 minutes or so.
8 minutes even, yes.
Okay. So this reduces the H0 tension and delivers a better fit to data. So let me mention some of the constraints, especially the observational consistency checks that you could apply to some of these effective field theories that you could construct. Let me, for instance, start with an example where you could apply the supernovae, the CMB, and the BAO data to constrain such theories. So I'm giving the example again with this cubic vector Galilean. As I told you, we have shown that this reduces the H0 tension and delivers a better fit to data. This was already only at the background level. So basically just the background evolution and taking the distance priors from CMB and supernovae. So you also, if you want to include all the fluctuations from the CMB, you have to take this theory and put it into a Boltzmann code. So this is what we did. So we compute the linear perturbations and embedded it into a Boltzmann code directly together with Hector. And here is a plot which summarizes the result, which is H0 versus the typical parameterization of the energy density of cold dark matter. And you can already see here very nicely that compared to the lambda CDM, which is the gray one here, together with Proca, you tend to go to higher H0 values. And this is the reason why it helps with the H0 tension. At the background level, the reason why Proca helps with the H0 tension is because it gives rise to a phantom-like dark energy equation of state. And at the level of the perturbations, of course, you have an additional degree of freedom, right? And then it has its own energy density and perturbation of velocity, which gives rise to additional effects. But already, as you can see at the background level, due to the phantom behavior, you push the value very easily of H0 to higher level values. Okay, then we have also the gravitational waves observations, especially the one coming from multi-messenger observations. I think Filippo will go more into detail of that. So with this gravitational wave observation that we had from 2 neutron star merging, we know that gravitational waves propagate with the speed of light. And this has huge consequences. So whatever dark energy model that you have, that you consider, has to give rise to a gravitational wave propagation speed equal to the speed of light. So for the scalar field, I haven't shown you even the covariant version, but these are this Horndansky Lagrangian. It gets rid of some of these operators. If you just simply say, okay, these are dark energy, it's supposed to be a dark energy candidate, and then you don't try to find the cosmological evolution where you can tune these functions in a very specific way. And also for the vector field, you can also simply get rid of some of these operators if you want to have a propagation speed equal 1. Okay, So there is this sixth operator that appears in this vector tensor interactions that doesn't have any effect on gravitational waves. So the gravitational waves still propagate with the speed of light, but it does have an effect on scalar perturbations. And this is something very different to the standard scalar tensor theories. All right. So one can also probe cosmological fields with gravitational wave oscillations. Let me mention that also quickly. So just to give you an example, imagine you have general relativity together with a Young-Mills field, some non-abelian gauge field. And now on top of a cosmological background, this Young-Mills field will give rise to a second tensor field. And if you have such a second tensor field, it can then interact directly with this tensor fields coming from the G mu metric, and you can have gravitational wave oscillations. The same thing can happen, for instance, in massive gravity. There you also have two tensor fluctuations in bigravity, for instance. And when you have this, if you have such a scenario where you have these two tensor fields, you can have such gravitational wave oscillations. This is just an example of a friction mixing, and you can already see the waveform is changed due to the oscillation between these two fields. And in this way, you can then go and look for such gravitational wave oscillations. Another very powerful thing that we can do now with gravitational waves is the luminosity distance. So once you have the amplitude of the gravitational waves, you can also compute the gravitational wave luminosity distance. In standard lambda CDM model, this equals to the standard luminosity distance coming from the electromagnetic part. And here you can then see this is the way how then the Hubble function relates directly to the gravitational wave luminosity distance. Now, if you have a model which is not lambda CDM and this is not equal, this would be a smoking gun for physics beyond lambda CDM. So, and we can also use these new observations of the luminosity distance of gravitational waves to hopefully also tell some independent information about the H0 tension. Just to give you another example here, if you had such a Young-Mills field, an additional Young-Mills field, then the ratio of these luminosity distances is not going to be equal 1, but it can oscillate. And so with some particular behavior, and that would be really a smoking gun for physics beyond lambda CDM, as I mentioned. Okay, I think I stop here and take some questions. Thank you.
Thank you very much, Lavinia, for the nice talk. So indeed, we have time for some questions. So if you want to ask something, please raise your hand. Okay, Tony has a question, so please go ahead.
Lavinia, so I have two questions actually. So the first related to the, I think you call it coincident GR scenario. And my question was, to what extent does that differ from sort of a Palatini version of GR, or is there some relationship there? It seems like there probably is. And the second question was about your massive Proctor theories, you know, your generalized Proctor, sorry. And I just wondered to what extent the transverse modes played any role. And obviously, I imagine most of the magic is in the longitudinal sector, but what role does the transverse modes play in that? So,
yeah. Concerning the first one, so yeah, in Palatini formalism, in the sense that in all these other formulations that I presented, the connection is treated as an independent geometrical object apart from the metric. So if you take general relativity in the standard way in terms of curvature and you write it in form of alla Palatini with an arbitrary connection, then the connection doesn't do any effects, not even to the matter coupling. And then you have just standard general relativity. You don't really change much. And so in the coincident general relativity, the connection from the very beginning is completely independent of the metric. And so it has nothing to do with the Palatini formalism of the Einstein-Hilbert action. But if you want, there is parallel, because if you don't assume that the connection is independent, and if you assume it's the Christoffel symbol, then you might even run into problem as soon as you start considering other Lagrangians, such like which might have other additional derivatives acting on the non-metricity tensor. So it's a Palatini formalism in the sense that you have an independent connection. Concerning the generalized Proca, the transverse modes, yes, you're absolutely right in the sense that at the background level for cosmology, they don't play any role, but there will be some small fluctuations also in the tensor modes. And when you look at the evolution of these tensor modes, imagine starting from CMB, what you see is that they very quickly decay away. However, on very small scales, when you study structure formation, they will have also some effects, some sort of a repulsive force on small scales, and because they have a very non-trivial interaction to the longitudinal mode, there is a complicated back and forth between the longitudinal and the transverse modes. But for the cosmological background, they don't matter.
Okay, thanks.
Excuse me, can I interfere a little? Because I don't have a hand, so I cannot really raise my hand. Just to point out that it's possible to have a homogeneous and isotropic universe even with non-zero, with a single vector field, with non-zero transverse components, if this vector field is oscillating. That is, if it's massive and it's actually oscillating very fast. And then, sorry?
That's true, yes, I forgot that,
Yes, so it's not the transverse components don't have necessarily to be zero, as long as they are oscillating very fast when this vector field becomes important. If it's unimportant, if it's a spectator vector field, then they don't have to be oscillating. But if it becomes important and they are not oscillating, then it breaks isotropy. But if it's oscillating, it doesn't.
So when they oscillate, I guess you want to use them for some dark matter purpose, or?
Well, they can actually, I have developed the vector curvaton mechanism a few years ago. They can actually introduce a contribution to the curvature perturbation. So in a similar form as the curvaton mechanism.
So if they couple to the curvature in a non-minimal way?
No, they don't have to couple to the curvature in a non-minimal way. They have perturbations. So you need a theory where the vector field obtains perturbations during inflation. So you need to break the conformal invariance of the vector field. But once they do, this means a perturbation in the amplitude of oscillations, which means a perturbation to the density of the vector field. So if it ever becomes important to,
you don't use the field for the inflaton field.
No. That's
so
why I call it a
curvaton. I was showing you was, if you want to be this field to be the propagate, to be basically the fundamental field to give rise to the self-accelerating solution. Then it needs to have a temporal component.
I understand, but I'm just saying that you can have vector fields playing an important role in cosmology and becoming dominant to the, as long as they are massive and oscillating when they do so.
Yes.
But they also cannot give you acceleration. That's true.
Yeah.
Thanks, Elias, for the for the comment. I had
Can you help me find the hand? Can you help me find
yes,
the
at
hand
the bottom,
so that I will not interject?
Yeah, at the bottom there are a
Yeah.
few options, starting with security, participant, chat, share screen, record, which you might not have, and one of them is called reactions. When you click on reactions, you should be able to either clap your hands, give thumbs up, but also raise hand, lower hand. It's under reactions.
Okay.
I can send.
I'm not seeing the raised hand. I can see clap the hands. I can see heart. Can see everything else. Anyway, I shouldn't continue interrupting. I'll find out on my own.
Well, we have 1 minute, but it's going to be a very quick question. You showed that there were some in those three equivalent formulations of GR. You showed that there were several numerical coupling constants, coefficients that had to be tuned precisely. Could you elaborate on whether the tuning is stable and whether there is some enhanced symmetry that keeps you there at that point, or it is unstable under, let's say, radiative corrections?
Yes, so if it's in the sense as in standard general relativity, as soon as you move to this very specific tuning of the coefficients, you have Lorentz symmetry appearing, you have diffeomorphisms appearing, and in this other formulation is exactly also in the same way. So it's a unique particular theory with enhanced symmetries compared to the larger, theories with different coefficients there. So concerning the quantum behavior of this three equivalent formulation, they will be exactly like in GR. They're only, an effective field theory, safe from quantum corrections up to Planck scale. But so yeah, there is not really a better quantum behavior version of this formulation.
Okay, thank you very much, Lavinia, for this nice talk. Thanks again. So I think now to try to keep